So then let's talk just a little bit about the mechanism for sintering. For mass transport during sintering, because sintering, we say mass transport because the material has to move from certain location to some other location during sintering. You think, okay, the elimination of the pores, the green growth, all these request the mass, the material, the atoms to move from certain location to some other location. Okay, and here we're talking about, let's think about the so-called vapor pressure over curved surface. We have, from physics, we have so-called Kelvin equation, which is relative pressure, take natural log, equals to 2 times surface tension times the molar volume divided by RT over radius. Okay, so that's Kelvin equation. And if we say we have material like this, which is essentially flat surface, R for radius of curvature is infinity. You have a flat surface. Your vapor pressure above it, your equilibrium vapor pressure above it is just your equilibrium vapor pressure, P0. Make sense? For any material, there's always some vapor above it. Any material at any temperature, except at ambient conditions, the vapor pressure is almost well, at atmosphere pressure, I'm talking about the vapor of this material is almost zero, like steel. The vapor of steel gas in over flat is essentially zero. Okay, at ambient temperature. Okay, but people find, okay, if we have a curved surface, depending which way it curves, this way, sticking out, okay, or you call it radius curvature positive. Radius curvature is positive. And then, based on this equation, if radius curvature is positive, the right side, the whole thing would be positive, which means your pressure over a curved surface would somewhat higher than when it is flat. Okay? And how much higher, depending on how curved you are. If your radius curvature is extremely small, which means your particle size is very, very small, the pressure over this particle is actually much higher than equilibrium. Make sense? On the other hand, if we have something like this, in this case, we would say the radius curvature is negative. This is the material. We are talking about for the material, the solid material. And in this case, if R is negative, this right whole side would be negative, which means the natural log is negative. The consequence would be the equilibrium pressure, or the pressure over this curved, concave surface would be smaller than equilibrium. Okay, so now you see we have flat surface, positive radius curvature, negative radius curvature, and they would have different vapor pressure around it. And here we are talking about, okay, room temperature is not a big issue, but at higher temperature you can imagine the difference between the vapor pressure can be significant at higher temperature. Make sense? So now let's think during sintering. We have two particles, and over here I have positive curvature, right? A positive radius curvature. And in here, if you can imagine, it's kind of locally something like this. Make sense? This is kind of what we people call neck location. In neck location, we are approaching something like this. Okay, and over here, the sticking out location, where we have positive radius curvature, we would have higher vapor pressure compared with flat. On the other hand, in the so-called neck location, something like this. we would have negative radius curvature as a result, lower vapor pressure. Higher vapor pressure in this region, lower vapor pressure in that region. And in terms of mass transport, naturally you can imagine the vapor would go from where to where? From higher vapor pressure to lower vapor pressure. That's what we call mass transport, right? Higher gas, whatever that material is, if there is vapor pressure, it has a tendency to transfer from here to here until everything becomes flat, equilibrium, right? That's when it stops. So that's what we said in this paragraph. Vapor pressure over particle with smaller diameter is higher than over larger diameter than over neck region. Essentially, here higher than here than here. So as a result, this becomes the so-called underlying driving force to drive the mass, the material go from here, sticking out location, sharp protrusion into neck location or cusp location. Okay? So this is one way to view what is driving the sintering process if it's going by vapor process. The other one is about vacancy. We said solid material, although most of them are crystalline, they always have some missing atoms, also called vacancy within them. And the vacancy beneath curved surface, whether it's solid or liquid, we are going to have similar related types of equation. The vacancy concentration versus equilibrium versus kind of flat surface is given by this equation with a negative sign there. Okay? And then flat surface, you have certain vacancy concentration, which goes to 0, which means you have flat surface. And in here, again, the radius curvature is infinity. If radius curvature is infinity, the right side is essentially 0, right? If the right side is essentially 0, which means the natural log is 1, which means CV is the same as CV0. Make sense? On the other hand, if we have something like this, a local protrusion or a small particle with a finite, small, positive radius of curvature. And in this case, if my R is positive, but I have a negative sign here, which means my whole right side is negative, it means over here, my vacancy in this location is actually lower. Vacancy concentration is actually lower than it is when it's flat. On the other hand, if we have a concave case, similarly, the radius curvature would be negative. And the radius curvature is negative, we become positive, which means over something like this, the vacancy concentration is actually higher than when it's flat. Vacancy concentration is higher than when it's flat. Okay, now let's think of, again, our two particles coming together. We said here, positive radius of curvature, right? For here. That means lower vacancy concentration for within the solid. Here, I'm not talking about vapor. I'm talking about within the solid, in this local region, within the solid. And then I'm talking about here, close to the so-called neck location, where we would have essentially negative radius of curvature, and you would have, for this region, higher vacancy concentration. Now let's think. We have less vacancy here, more vacancy here. Which way would vacancy diffuse? From high to here. Or vacancy diffuse, the other way to say is which way would mass, the material, the atom would move? Opposite, right? Yeah, vacancy goes here, the material goes the other way. So you see, when we start to consider vacancy or atom movement within the material, this time we are not talking about it goes through the gas phase. Within the bulk, within the lattice of the material, we would have the solid, the atoms would move from low vacancy concentration to high vacancy concentration until everything become flat. Make sense? So this is essentially this paragraph. Vacancy concentration in region with smaller diameter is lower than over planar than over neck. And as a result, this becomes another driving force for atoms to move. But the net effect is the same. The atom would move from small positive radius curvature to negative radius curvature. Make sense? So in both these, you see the same trend. The atom will move either through gas phase from here to here or from bulk. They're moving in the same direction.